For this experiment, we are trying to find the moisture content of aggregates. This test is important for strength and durability analysis of concrete. It is also vital for concrete production to know how much water is needed to be added to a mixture. A high water-cement ratio will weaken the concrete, while a low water-cement ratio will strengthen it. This method is sufficiently accurate for usual purposes, such as adjusting batch quantities of ingredients for concrete. For the fine aggregates, the amount of sample collected was placed on a pan to pile up and was then flattened out to form a circular figure. The figure was then divided into 4 sections. 2 sections opposite to each other were removed. The other 2 remaining sections were placed in a container. The container with the sample was weighed and then placed in the oven to dry. For the coarse aggregates, the amount of sample collected was placed on a pan. Samples were then dropped on a splitter, which has 2 containers below it. Each container, more or less, should have half of the sample originally collected. One of the container was weighed and placed in the oven to dry out. The group then waited a day to remove the samples for both fine and coarse aggregates from the oven. The samples from the oven were weighed and were compared to the original samples to calculate for their respective evaporable moisture content.
Experiment 2 and 3. Sieve analysis of fine and coarse aggregates. ASTM-C136. The procedures were similar for both samples, but the only difference is the sieve numbers used. For the fine aggregates, the sieve numbers used were 4.75 mm, 2.36, 1.18, 0.6, 0.3, and 0.15 mm. While for the coarse aggregates, the sieve numbers used were 25 mm, 19 mm, 12.5, 9.5, 4.75 mm, and finally 2.86 mm. For the procedures, after weighing the collected samples for both fine and coarse aggregates, the sieves were organized from the largest to the smallest size. Then, the samples were poured on the sieves and placed in the mechanical shaker for 2 minutes, so that the particles would automatically fall. Then, each sieve was shaken manually in order to have a more accurate data, and to make sure that the samples are thoroughly sieved. Finally, each sieve was weighed in order to obtain the amount retained in that particular sieve. Considerations: 1. Make sure the sieves are in the proper order. 2. After using the mechanical shaker, the process of manually shaking the sieves is very important. This is to make sure the samples are thoroughly sieved. 3. The weight of each sieve should be taken to obtain the amount retained in order to calculate the cumulative retained and also the percent passing for each sieves. Established values: finest modulus 2.3 to 3.1. Max size of the coarse aggregates 37.5 to 9.5 mm. Absorption 0 to 8%. Bulk specific gravity 2.3 to 2.9. Surface moisture content for the coarse aggregates it was 0 to 2%. For the fine aggregates 0 to 10%. Significance: sieve analysis of coarse and fine aggregates are important because it can give an overview of the grading of the particle size of a given sample of aggregates. Well-graded aggregates are desired because the different sizes of aggregates create an interlocking effect and thus increasing the strength of the concrete. Meanwhile, the finest modulus is an estimate of the coarseness and the fineness of aggregates, and is also significant in determining the workability of the concrete that will be produced. Application: sieve analysis can be used in environmental engineering and also in pollution engineering.
For this experiment, we are tasked with finding the specific gravity of coarse aggregates. This is important in concrete mix design to be able to convert volumes into weight when calculating ratios. If the aggregate is within the ideal range of specific gravity values, it can be concluded that the aggregate can be used in producing high-strength concrete. Absorption of aggregates is also an important property. It is expected to be lower in value to be able to accurately estimate the water-cement ratio. Aside from mix design, this test is also used for material property change identification and deleterious particle identification and separation. For the first step, coarse aggregates were removed from the bucket and transferred on a 4.75 mm sieve to have the correct size of sample. Next, a piece of cloth was used to wipe the coarse aggregates. before transferring them on a pan. This is the saturated surface dry condition, or also known as SSD. The coarse aggregates were then weighed in water in a wire basket. Finally, the coarse aggregates were transferred back to the pan, dried in the oven to be weighed afterwards.
The experiment 5 is on the specific gravity of fine aggregates based on ASTM C128. For the procedures, the first step is to sieve the aggregates to ensure that they are in correct sizes. Then, place the sand on the wide pan and dry the aggregates using a blow dryer until the sand reaches saturated surface dry or SSD condition. To test whether the sand is on SSD condition, a sand cone test was done. The sand cone test is done by tampering the sand in a cone mold for every third of the height of the cone. Once full, the mold is removed. The sand sample will slump and it must be dry enough that one top will let some particles fall off. However, great amounts of slump is also avoided as this means that the sample is too dry. The sample that passed the sand contest will be transferred in a separate pan and weighed. Then, the sample will be transferred slowly to a flask partially filled with water. The flask will be put under a vacuum to release the air particles present in the water sand mixture. The flask is then weighed and then the sample water mixture is placed on a separate pan to be dried at the oven. The dry sand is weighed after 24 hours. For the considerations, the production of the SSD condition is important as absorbed water can affect the value of the calculated specific gravity. The sand cone test must be done correctly as it can give false SSD condition. Additionally, during the transfer of the sand to the flask, it is important to make sure that all sand particles are submerged in the water and not on the surface of the flask. For the established values according to the American Concrete Institute, the specific gravity of aggregate suitable for concrete mix is between 2.3 and 2.9, while the absorption is between 0 and 8%. For our experiment, the values calculated is 2.457 and 3.44% for specific gravity and absorption respectively. The specific gravity is important to be within acceptable range as it greatly affects the strength and compacting factors of the concrete mix. Absorption, which was calculated using the weight of the SSD and the oven dry condition, is also important as it affects the water requirements for a specific concrete mix to maintain a specific water-cement ratio. The applications of this experiment include mix design of concrete and the conversion of volume into weights and vice versa.
Experiment 6. Specific gravity of cement. First, clean the flask with a piece of cloth. Then fill the flask with kerosene. Next, place the stopper on the flask and put them in the water for 5 minutes. The temperature of the water should be kept around 20 degrees Celsius. Repeat the procedure until 3 similar readings are achieved. Then, prepare an amount of cement of around 62.4 grams. Next, put the cement inside the flask containing the kerosene. Then place the flask with the cement and kerosene in the water and keep the temperature of the water to 20 degrees Celsius. Repeat the procedure until 3 similar readings are achieved. Lastly, remove the cement and kerosene from the flask. Clean the flask using a piece of cloth. Estimating the specific gravity of cement is essential because it determines the effects of the surrounding atmosphere to the moisture content of the cement. This experiment can be applied in order to determine whether the cement has extreme moisture content. There are some considerations to be made when performing the experiment. One is to always make sure that the flask is clear of any water. When the group was ready to add in the cement, they found out that there was a single droplet of water under the flask. This means that they had to repeat the whole experiment or else the cement would have hardened inside the flask and eventually break it. So it is always important to be aware when dealing with the flask, especially during the cold bath. There are some values that are established in this experiment. The specific gravity of Portland cement is 3.15. The Portland blast furnace slag and Portland pozzolan cements have a specific gravity of 2.9.
For this experiment, we are tasked with finding the unit weight of aggregates. This is important because knowing the unit weight of aggregates would give information on the amount of air voids present in your aggregate sample. This is reduced by using different compacting methods like jigging, rodding, and shoveling. If there is a small unit weight measured, it means that less air voids are present, therefore encouraging more contact in between aggregate particles that would result to a better interlocking effect. This improves the overall strength of the produced concrete. For coarse aggregates, all three methods were used. For fine aggregates, only the rodding method was available. These are based on standard testing methods. For the procedure of the experiment, the rodding method was done by filling the container with 1/3 sand and rodding it 25 times. This was repeated for 2 more times until it was full. 3 trials were done for the fine aggregates, while only 1 trial was done for the coarse aggregates. Similarly, the jigging method was done. It was done by filling the container with 1/3 full, then it being jiggled 50 times. Again, this was repeated for 2 more times until it was full. The shoveling method was done by filling the container and patting it down using a shovel. Afterwards, all the outputs of each trial were weighed.
Procedure for selection of mixed proportion. The first step is to consider the choice of slump, which depends on the structural specification. Second step is the choice of maximum size of aggregates, which depends on the largest economically available and should be consistent with the dimension of structure. Third step is estimating of mixing water and air content. Quantity of water per unit volume of concrete depends on maximum size of aggregates, particle shape, grading of aggregates, concrete temperature, amount of entrained air, and chemical admixture. Step 4 is the selection of water-cement ratio. The choice depends on strength requirement, durability, workability, and finishability. Step 5 is required cement content, which can be obtained by dividing the volume of water by the water-cement ratio. Step 6 is the quantity of coarse aggregate, which is estimated in terms of percentage of coarse aggregate inside a well-compacted concrete mix. Step 7 is the computation of required fine aggregate. The next step is the adjustment according to the moisture content of fine and coarse aggregates. And then, the next step is for the laboratory trial mix, wherein the volumes are scaled down to about 20 liters or 0.02 cubic meter. Step 10 is the carrying out of trial batch test. The water required is being checked and then add necessary water to obtain slump and air content. If the slump of the trial batch is not correct, increase or decrease the re-estimated water content. Control the introduction of fine and coarse aggregates to achieve the desired finishability and workability. Reduce the amount of aggregates if the required slump or required cohesiveness cannot be achieved. In this experiment, it is quite important to consider factors such as the water-cement ratio, volume of water, aggregates, and cement. The common established values in the mixed design of concrete are the size of the fine and coarse aggregates, unit weight of coarse aggregates, bulk-specific gravity and absorption of aggregates, mixing water requirements for a given type of aggregates, relationship between strength and water-cement ratio, and specific gravity of cement and pozzolan. This is to analyze the merit and demerit of design and control of concrete production as required by the structural requirement. This analysis is important to determine the physical and geotechnical properties of the materials needed for the mixed design in order to attain the required data for the design procedure in accordance to the parent material types and location and the specific density of the design concrete that will be suitable, adaptable, durable, economical, workable, and generally safe for the structural design objective of the weather condition in any specified locality. Concrete is comprised of several materials that interact with one another to produce a material with cementitious properties. These added materials to produce concrete greatly affects one another, and this interaction is what results to the fresh properties of concrete. Trial mixes and fresh properties of concrete is done by preparing a proportioned batch and placing the mixture to butter the mixer. Next is to prepare the amount of fine aggregates, coarse aggregates, cement, and water. Add 50% of coarse aggregate in the mixer, followed by 100% of the cement, and finally 50% of fine aggregate and dry mix for 1 minute. Add 100% of water and mix for 1 minute. Then gradually add the remaining coarse aggregate and fine aggregate, mixing 30 seconds for each. Run the mixer for 3 minutes, followed by 3 minutes rest, and finally 2 minutes final mixing. Perform the slump test and then test for air content. Lubricate the molds and then place the final mixture into the molds by layer. Each layer should be distributed equally by using a thumping rod. Some of the materials that are added to form concrete and affect its properties are water, coarse and fine aggregates, cement paste, and other admixtures if present. The concrete mix design proportion can be based on the mass of the volume of each component. However, the water-cement ratio proportion is commonly based on the mass of the materials used in the mixture. The mixture of the materials is a delicate process because this phase defines the workability, compressive strength, and durability of the product. The experiment aims to expose the students to trial mixes of materials needed to produce concrete to make use of the concepts involving the concrete mix design. After the experiment was conducted, the students are expected to determine the exact amount of proportion of the constituents for concrete mix such as water, cement, coarse aggregates, and fine aggregates, and then to produce concrete given the specified measurements for trial mixing, and then to form a satisfactory end product of concrete such as beam, column, or slab as economically as possible. The civil engineering students can now apply this on their future concrete mixing and make sure the water content is properly monitored and compensated to properly ensure the quality of the concrete. Batching plants, however, have extensive data on concrete mixes, thus mixing concrete based on the specifications are much easier. However, for the non-ready mixed concrete, this knowledge and experience will be of great tool for future concrete mixings.
Experiment 10 is about making specimens as reference to ASTM C192. Creating the specimens or the concrete cast is essential in the progress of the strength of the concrete. In this process, the molds are filled up with concrete, and this has to be done carefully as to avoid as much air voids as possible. The curing process is also done in this experiment and is also essential because it is a segment wherein the strength of the concrete truly develops. Curing is also done to control the desired moisture and temperature conditions of the specimen. The size and shape of the mold is determined by the type of loading that will be done on the experiment. To accomplish the experiment, 4 containers or molds were used to hold the concrete mix, 3 of which were in a cylindrical shape while the 4th one was in a rectangular shape. They were first cleaned and then lubricated with oil before placing the concrete. After obtaining and producing the correct proportions of the concrete mix, it was placed in for the molds. A tampering rod was used to evenly distribute the concrete in the molds. The concrete mixtures were then placed aside for 24 hours to harden. After that, the concrete specimens were taken for curing. It is important to consider that the containers or molds must be first cleaned to be free from impurities and voids. The interior of the molds must be lubricated with oil prior to the pouring of the concrete mix to prevent the sticking of concrete on the surface of the mold. Then, the concrete must be poured evenly and constantly tampered to distribute the concrete and get rid of as many voids as possible. After this process, the concrete mixtures were then placed aside for 24 hours to harden. After that, the concrete specimens were taken for curing. Concrete is typically cured for 7 to 28 days depending on the property that will be tested. The longer it was submerged in the water bath, the stronger the concrete. This water bath will maximize the hydration of the cement in the concrete. Some of the applications of making specimens include in situ curing of columns, beams, or slabs by spraying curing compounds or by wet burlaps. Another is curing of specimens of the actual structure to ensure strength capacities. Molding and curing is typically done on slabs on ground like pavements, sidewalks, parking spaces, driveways, floors, and canal linings. Also on structural concretes like bridge decks, piers, columns, small footings, and retaining walls.